So this is going to be a short video on free body diagrams and how you can hopefully never mess them up again, because I know I had a lot of trouble getting them right in a lot of my classes. So let's take a simple situation here. We'll take a box on a plane, an inclined plane, right? So let's draw an inclined plane here, right? And make that a little darker. And then there's going to be a box on the plane, right? And the plane is going to be on an incline of what we'll call theta for that angle measure, right? And then so what we're going to do is we're going to say that this box has a mass of m, right? And this surface has a coefficient of friction of mu, right? The Greek letter, it's a lowercase mu, right? So, and what we're going to do is we're going to start by drawing force of gravity, right? We'll do the easy one first, right? Which we can call F sub g, or I like to use W, right? But that's always going to be equal to your mass times acceleration due to gravity, or g, right? So there you have weight, right? And then you know that you need a normal force, which is the force that the surface exerts upward on the box, right? So that's going to act perpendicular to the surface. So if this is the line perpendicular to the surface, if this is the line parallel to the surface rather, and we line it up with that line, so these two lines are parallel, then the normal force needs to act in a way that it's perpendicular to this red line. So that's going to be our normal force, and we can call it F sub n, or I like to call it just capital N. That works too, right? And then now, since we know you have a coefficient of static friction given, you know that there's going to be friction on this surface. So if we were to allow this thing to slide, and it started sliding, it would slide in this direction, right? So friction needs to act against that motion. So friction always acts against the motion of an object if it's in contact with the surface, which in this case it is, right? So friction needs to act against the motion of the object, which means it acts in this direction or sort of towards the right. So you can draw friction as acting in the center of the object or on the point of contact with the object on the surface, but for simplicity I think it's just easier to draw friction acting at the center of the object. So we'll call that force of friction, or you could call it F sub F, or you could call it, I like to give it the little script F, right? And we know that force of friction from your reference sheet is equal to mu times N, mu times the normal force, right? And then now if you wanted to find the normal force, you know that it's going to be a component of your force of gravity, right? Because otherwise you would have acceleration in what we can call the y direction as being this way, not just straight up and down, but sort of in this direction, right? So we're going to make components for our force of gravity, and you know that because these are components of the force of gravity, that their magnitudes can't be longer than the original force that you've drawn. So you create a right triangle, right? And we'll call this force F sub y, that acts in the what we'll call the y direction here, and we're going to call this force that acts in the x direction F sub x. Okay, so that's F sub y and F sub x. Now you know that, let's say you're tasked with finding the normal force. Well, you know that the normal force is going to be equal to F sub y, so if you were going to sum the forces in the y direction, which we can do, and we know that they have to be 0 if there's no acceleration, because let's just say that this is a stationary object, right, so not moving, right, so then the sum of forces in the y direction have to be equal to 0. That means that Fy, you could say negative Fy plus n has to equal 0. That means Fy has to equal n, right? You move Fy over to the other side, Fy has to equal n. Now if you want to find n, you need to find Fy. And Fy is a component of the force of gravity, which is equal to mg. So Fy is going to be mg times something, which is going to be it's going to involve a trig function, which I'm sure you've seen so far. That's how free body diagrams normally work out. Now, you know that it's this side of this right triangle, and this is the angle theta. Now, you can prove geometrically that this angle theta is this angle here theta, because they're what's called alternate interior angles, but that's not exactly important to do, and in fact, 99% of the time, this angle theta will be this angle theta in terms of the components of that force. So we know that Fy is going to be mg times the component of something with respect to theta. Now, because this is Fy, and this component acts adjacent to this angle theta, not opposite, but adjacent, we're going to say that Fy is equal to mg cosine theta, right? Because cosine theta is adjacent over hypotenuse. Adjacent over hypotenuse would be Fy over Fg, and you rearrange a little bit, you get Fy equals mg cosine theta. Now, this is, I think, a good time to bring up, I know in some places, in some high schools and colleges even, they'll write on your reference sheet something like Fx equals F cosine theta when you're going to break up forces into components, and Fy equals F sine theta, right? That's something that they like to, that a lot of reference sheets that I've seen online, actually, from high schools and some universities also have. This is not correct. That might be the case for when they give exams, but that's not the case in general, and that's not a good rule to follow. You see, in this case, we can call this the y direction, but Fy is not F sine theta. Fy is F cosine theta because it's the component adjacent to that angle theta, right? So that's how to find your forces in the y direction. Now, if you want to find your forces in the x direction, now the x direction is, here's where we'll call, and I'll label, this is going to be the positive x direction, this is going to be the negative. This isn't a proton and electron, that's labeling the positive and negative direction for the x direction. So, and we're going to sum the forces in the x equals 0, right, because the object is stationary. So in that case, well, we have friction acting in the positive x direction, right? And then we have this component, f of x, right, acting in the negative x direction. So to write that out, if we wanted to write the components for f of x, well, f of x is the component that acts opposite the angle theta, so that's going to be the magnitude of the force, or mg, right, which is equal to the weight, times the sine of theta. This component acts opposite that angle theta. So this is going to be sum of the forces in the x direction equals 0 equals friction in the positive x direction, and then f of x acts in the negative x direction, so let's say minus f of x, and then when we sub it in, f0 is f minus mg sine theta, right, which we just found over here. So then you bring mg sine theta over the other side, then f equals mg sine theta, right? And then from here, this is a general free body diagram that you can solve most Physics 1 free body diagram problems as a sample with. So you draw your forces, you label your components, you write out some of the forces in the x and y, and then they might just ask you what's the acceleration of the object in the x direction, or something like that. Well, then you know the acceleration of the object in the x direction is equal to, well, if f equals ma, right, then a equals f over m. So acceleration in the x direction is the force in the x direction over the object's mass, right? Then you know you just sub in numbers. And that's part of the reason why solving things algebraically can be a little more useful, because you don't need numbers to be able to solve the problem. You just need to be able to represent it in terms of variables, and then you can just plug things in afterwards. So hopefully that gives you a better understanding of free body diagrams going forward in physics.